It's my pleasure to present my recent work entitled Non-Local Problem for the Time-Fractional Diffusion-Wave Equation. This work is devoted to analysis of existence, uniqueness, and regularity of solution for class of non-local boundary problems. And this is outline of my talk. First, I will briefly introduce the problem. Then I will discuss some known results. Then after that, we will present some preliminaries and assertion, which is we will use to get main results. Finally, we formulate main results of this work. So we consider the following time-fractional diffusion-wave equation with non-local initial non-local condition in time. The equation involves the Caputo-fractional derivatives. Sometimes some literature calls Gerasimov Caputo-fractional derivative. And you know, this derivative combines the diffusion and wave equations, properties of diffusion and wave. And the main problem consists of a fractional evaluation equation with two non-local conditions at times 0 and final time t. And the parameter gamma is non-zero, real number. Phi and psi f of t are given functions. And in the equation, operator A is assumed to be positive self-adjoint with compact inverse on some separable Hilbert space, which allows us to use spectral decomposition and Fourier series techniques. And here the notion of definition solution of our problem one. I mean, a function u intersection of these function classes with the properties and satisfying conditions one is called the solution of the non-local problem one. So our main focus solve problem one, and here are some results. There are main classical results. For example, for parabolic case, we can see first work by Professor Asharif, Fanalif, and Soboleski. But our work mainly nearly to the second work, and here afterwards Professor Asharif and Sadibek investigate the following problem for elliptic equation, second order elliptic equation with positive operator A with two non-local boundary conditions. And here after studied well-postness of this problem. And the third work Professor Asharif and Soboleski, and there are such type problems also considered. But in fractional case, we can see the fourth work, academician Alimov and Professor Ashurov considers the following backward problem. And here, derivative by means Caputo-Gerasimov, an operator also has the same property as we state below. And here, after consider the backward problem for the time-fractional subdiffusion equations. And the fifth work, Professor Ashraf and Faiziv considered non-local problems in time for fractional subdiffusion equations if beta is equal to 0 and zeta equal to capital T and final T, then we can also get a backward problem. And in usually backward problem is ill-posted by Adamar. Therefore, such type problems are studied more difficult. But our approach more near the last work. I mean, in the work of Florida and Yamamoto, and they investigated the following diffusion wave equations with final time conditions. And as we said, this problem is called backward problem. When alpha greater than 1 and less than 2, then this problem also well posted for positive T not belonging to countably finite set. Even non-unique occurs for such exceptional values of T. So preliminaries, and we introduce fractional power of operator A and the domain and its norm, and also we introduce the Hilbert spaces, Hilbert continuous spaces, and absolute continuous functions, which we will use below in these spaces. So first, we consider the following scalar fractional ordinary differential equations 2 with nonlocal boundary condition 3, where lambda, gamma, and b are given real numbers, and moreover, lambda strictly positive, gamma does not equal to 0. Then we have the following, we can say a solution, but now, frankly speaking, I'm afraid to say this solution, the problem 2 and 3, because the right side involving the function rho eta given by 5. This function involves in the denominator. It may has some zeros. Therefore, first of all, we should analyze zeros of this function. Here, our first main result, lemma about zeros of the function rho eta. For non-zero gamma, the set P is non-empty and finite. Moreover, there exists a larger constant positive C1 such that the inequality 6 holds. And this lemma allows us to show the uniqueness and existence of our problem. And therefore, first, I should prove this lemma. And this lemma proved by using expansions of Mittag-Leffler functions. And here, given the expansions of Mittag-Leffler functions, 1 and 2 parameters, given as 7, and we put each expansions in 5. Then we can get the following asymptotically expansions when eta tends to infinity. And this rho eta, you can see main part depends on gamma. Its sign. Therefore, each cases separately we study. First case, let gamma less than -1 or strictly positive. When gamma less than -1 and alpha in our case is greater than 1 and less than 2, and by properties of gamma function, Euler's gamma function, this is negative, and gamma is also negative, and this ratio positive. Then there exists a constant, a positive constant m, such that rho eta is positive for sufficiently large eta. And moreover, since rho at 0 equal to gamma plus 1, and by the continuity of the rho in a half axis, we can find a sufficiently small constant epsilon, such that rho eta be negative for this interval. And then we can use intermediate value theorem yields that there exists eta null in this interval. This eta null function will be 0. Moreover, since rho eta is analytic in segment, I mean the set is finite. Otherwise, rho eta is equal to 0. Each eta, which implies at 0 rho eta equal to 0 by the continuity of rho at eta equal to 0, which contradicts rho 0 equal gamma plus 1. In the case gamma positive can be shown in a similar manner, but the second case, when gamma in this interval negative, but greater or equal to -1, we cannot say any information like above. But if function 5, I mean rho eta has zeros, then they are finite because it's analytic. To do this, we calculate the integral of the function 5 in a finite interval from 0 to m, and study its behavior for larger gamma, larger lambda. By 5 and 7, we obtain, and here we put Mittag-Leffler's asymptotical expansions, and we get the following equality. And you can see the main term is also negative, so the function 5 has 0. Here is a figure. So we set zeros of the rho eta function. By lemma 1, we have no information on the number n of zeros of rho eta except it exists. But now we can provide an upper bound of the largest zero and eta n. Therefore, for convenience, we set the following numbers. Then we have, by definition of alpha and Euler's gamma function, each numbers mu1, mu2, and mu3 are positive. Moreover, we set angle eta. By L, we denote the contour and complex plane, which is direct from infinity e power minus e eta to infinity e power e eta, and consists of the following contour. And this contour may see in the book Digerbashian. Here we draw by black line. Moreover, we set nu1, nu2, and nu3. Since there exists a constant C0, positive C0, such that expansion is less than for any point in contour, we can directly verify that each values, each numbers nu and nu1 and nu3 positive and finite. Next, we can say upper bound of the zero of the function rho eta, let gamma positive, then the maximal zeros of the function rho eta satisfy the following inequality. For the proof, we use the following formula for Mittag-Leffler functions, which is given the book written by Igor Podlubny, where mu1, mu2, and mu3 defined below. And also the functions E alpha G and E alpha alpha defined by integral. Then this integral may estimate by the following 11, and these estimates are obtained by Florida and Yamamoto. Then using these inequalities and using expansions of Mittag-Leffler functions, we put these estimates and expansions, and then we can get the following inequality. For eta greater or equal to 1 over model cosine theta, and it's also greater than 1, then we can write this inequality as the following form. In the brackets should be negative, therefore we can calculate. We just write in the brackets less than 0, we can get this estimate. Now we turn to show existence of the solution, the problem 1. And we know by the definition of operator, the equality is valid. Hence, in view of Fourier expansion, we can write the function by the series, by the Fourier series. Then where un of t is a Fourier coefficient of the function u, then we put equation which is given 1, then we can get the following scalar ordinary fractional differential equations with nonlocal boundary conditions. And using 4, which is given by, we denote by yt, because for each n, this problem has 2 and 3, then we can get, using this, we can get formally solution of the problem 1, which is given by 12, where capital P1, P2, or P5, they are operator function defined by the following series. And also, in the denominator appears rho eta, therefore we set lambda, and moreover this lambda is a countable set, and moreover lambda has an accumulation point 0, therefore all its points consist in the segment on this segment. Now we state the first auxiliary result. Let gamma is not equal to 0 and capital T does not belong to lambda if phi psi and in this class and f essentially bound in T, which values the domain of the operator A, then there exists a constant, positive constant, such that we can get the following inequality, which is given 13. Whereas C0 depends only gamma, alpha, and T. Now we prove this lemma. For this, we use the following lemma 4. Lemma 4 and a definition P1 also by the generalized Minkowski inequality. Okay. We can easily get the following inequality. Each operator function, for each operator function, we use the same method. I mean, we use lemma 4, our main subject. Lemma 4 and generalized Minkowski inequality. Then we can get certain inequality. I mean, each estimates are approximately the same because if you let me, I do a main result and let gamma does not equal to 0 and T does not belong to lambda. If phi psi in this class and f in T essentially bounded and valued the a power 2 minus 1 alpha, then the problem 1 has a unique solution. The solution is intersection of these classes such that its fractional derivative also continues on half interval. Moreover, there exists a constant C0, C1, positive constants, such we can get following inequalities, which is given 20 and 21. Moreover, it is our second result. Moreover, if phi is classes of the domain of the operator, but psi is in other domain of the operator, a power 2 minus 1 alpha, and f means source term is absolute continuous with value dA power 2 minus 1 alpha, then there is a unique solution to 1 satisfying and the following condition. I mean, the solution will be AC2 and intersection continuous at the same time, and its fractional derivative will be essentially bound in T, which values H. And moreover, we have the following estimates for fractional derivative. Our third result, if phi and psi are in domain of operator A and f is in Holder continuous with exponent alpha minus 1, then for the solution u given by 12, we have the following inequality 23, where C3 is a positive constant, and this constant does not depend on phi psi and source term. And from these main results, we readily get a corollary. And here also let gamma does not equal to 0 and T does not belong to lambda. Let phi and psi in the domain of the operator A and a source term equal to 0. Then there exists a constant C4 positive constant such that the solution will be infinitely continuous differentiable in the half interval. Moreover, this not only the solution, its derivative may bound by 24. I mean, in this corollary, we can see our solution will be asymptotically stability. So now we turn to prove our first main result. We begin by proving the uniqueness of the solution to problem 1. And also in here also we use a standard technique. Suppose we have two solutions which is they are not equal each other, and set Vt its difference. Then we have 25. Then we set Vn by for a coefficient of V. Then from equation 25, we can get for any n the following scalar ordinary fractional differential equations, homogeneous fractional differential equations, and the final time condition implies the following. Therefore, we get the following problem, which is given 26, and by our assumption t does not belong to lambda, then by 4 problem 26 has only the trivial solution for all n. Then by general theory, I mean by Parseval's identity, we obtain v of t identical to 0 for all t in the interval from 0 to t. Hence, the uniqueness of the solution is proved. Now we turn to get, now we show the existence, and we will more attention to get our main estimates. First, if phi and psi and f is shown classes, then the solution will continuous. And the following equality holds. 27 is boundary conditions. First, we show these assertions. Indeed, by lemma 4, we have for P1, we just estimate using lemma 4 and a generalized Minkowski inequality. And then we can get the inequality 28. And similarly from P2, the same as the proof of 16, we have P2 29. And so on. And for P3, we can get the same as above. And here, P4, we estimate in the domain of the operator, which is, we use lemma 4 and 15, and we can see its estimates, which is given by 31. Similarly, we can show that for P5 in the domain operator A, and combining these estimates, 28 and 32, we have 33. I mean, the function, if the initial data and a source term are required spaces, then we can see the solution is belong to the domain of the operator. Now we can show the boundary conditions which satisfy the solution. Therefore, we just write these terms and put its definition of P. Then we estimate each terms in the domain of the operator, and here we can see if initial data and source are required spaces, and we can see the left-hand side is finite. And here therefore we can use Lebesgue's dominated convergence theorem and pass to the limit, and we can get the first condition 27 the same. We can get the second, and now we will show the first we show the solution is 1 times differentiable in T. Then we can show the second boundary condition, which is given at 27. And for this, we use the following lemma 5 and lemma 6, which is auxiliary lemma. Then by generalizing Minkowski inequality for 1 times we differentiate 1 times P1. Then by the generalized Minkowski inequality, we can get estimate which is given 35. Moreover, applying lemma 5 once more, we can get 36. And here we used 11 and this embedding for alpha. Similarly, we have P3. Furthermore, by defining P4 and using lemma, and also we get P4 following between 38 and 39 inequality. And also once more using lemma 5, we can get for P5 operator function 40 and 41 inequalities. And it follows this as from a relation 28 and 32 and 35 and 41 that our solution the 1 times continuous differentiable in T. Moreover, the second relation, second boundary condition given in 27 may get analogously. Consequently, inequality 20 is direct consequence of 33 and 35, 41. Now we may show the second estimate. Therefore, here we assume phi and psi are the domain of the operator and have essentially bound in T. Then the same operation we can do, and we will get 42. In addition, from equation 1 and 42, we obtain 43. In the following, we improve the regularity of the solution U such that its fractional derivative is well defined by the capital fractional derivative. For this, by lemma 6, we have the operator function is absolutely continuous, and we can use lemma 6. Then we find its fractional derivative of order alpha as 44. And we see from the last formula in 28 that fractional derivative of this operator function is continuous. And from lemma 5, we know the second derivative of P2 phi satisfies the following equality. Then by 6 and 11, we can estimate the same as shown above. And here also we use some estimates. Then we can get the estimate 45. Thus, alpha is greater than 1. And here we can, the power of t appears alpha minus 2. And we can see this function is integrable. I mean, 2 times differential of P2 is absolutely integrable. And from it, from this, we can see P2 is RC2. And the same calculation we do for P3 and for P4 and also P5. Each estimates appears t power alpha minus 2. As we shown, this integrable function. Therefore, from this, we can see each operator functions is RC2. And then adding the 44 and 15 and also 1, we obtain the fractional derivative of when phi and psi are in the domain of the operator and phi source term absolute continuous function. Then solution will be its fractional derivative will be essentially bounded with value h. Now we prove the solution is in Hilbert continuous with exponent alpha minus 1. Therefore, let us consider 2 points on the interval 0 and t. Just we write its difference, and we estimate its brackets appropriately functional spaces. And here all written. And here we estimate in the domain of the operator then tends to 0 as h2 tends to 0. Then we can get estimate 52. And also here use some elementary calculations for E1 and 2. We can get estimate which is given 53. For other terms, we can get 54 and 55. And others also we can get these estimates. You can see each estimates h power appears the same number alpha minus 1. Therefore, from this we can conclude that our solution is Hilbert continuous with exponential alpha minus 1. And here shown its fractional derivative. Also Hilbert continuous. And from these estimates, we can summarize our solution, if phi and psi are the domain of the operator A, and a source term in this class, our solution will be Holder continuous. And this is the proof of theorem is complete. And thank you for your attention.